Okay, Algebra 1B students, today we are going to talk about Lesson 7-2, the first part of multiplying powers with the same base. So please open with me in your books to page 425. That's where you'll find the beginning of this section. Hopefully what we do today is pretty straightforward, potentially with the exception of our last example, but we will cover that when we get there. For right now, we're going to look at this essential understanding paragraph that you see right there in the middle of page 425. That paragraph says that you can use a property of exponents to multiply powers with the same base. Okay, so we're going to learn a new property of exponents today, and we're going to see exactly how this works here throughout the rest of this page 425. Okay? It also says that you can write a product of powers with the same base, such as, here's our first example, 3 to the 4th times 3 to the 2nd, using one exponent. All right? So look with me here at this equation here in the middle of your screen. That tells me that 3 to the 4th power times 3 to the 2nd power is really taking 4 3's all multiplied together, that's here, 4 3's multiplied together, and timesing that then by 2 3's multiplied together, okay? And now your book's claim is that that equals 3 to the 6th power, and they are exactly right. Hopefully you can see that there are 6 3's multiplied all together there, so this is now 3 to the 6th power. Right? We will see exactly how that works after we generalize this to our rule. All right? So here it is. In general, an equation like the one we just looked at, 3 to the 4th times 3 to the 2nd, which ends up equaling 3 to the 6th power, can be written using these variables that you can plug any exponent you want into. Okay? A to the m power, some number to the m, times some number to the n is equal to that same number to the power of these two numbers added together, m plus n. Please add that equation to your notes. Get rid of that there, not sure what that's doing. All right, add that equation to your notes there, please. A to the m times a to the n equals a to the m plus n. All right? Now, let's figure out exactly why that works. Okay? I'll leave that up there so you can keep adding that to your notes. Hopefully you've paused the video and done that already. 3 to the 4th power, as we mentioned before, is really the same as 3 times 3 times 3 times 3. And 3 to the 2nd power is 3 times 3, just 2 times. All right? So now when we go down here and talk about multiplying those two expressions together, I have 3 times 3 times 3 times 3 times 3 times 3. Now, we should know that these parentheses around all of that multiplication don't really help us with anything because it is all multiplication, right? So we can eliminate those parentheses, and then we just have, as I said before, 6 3's all multiplied together, 4, 5, 6 of them. 1, 2, 3, 4, 5, 6 3's all multiplied together. And we know that that written as a power is 3 as a base to the 6th as an exponent. Okay? So we started here with 3 to the 4th power times 3 to the 2nd power. We ended up at 3 to the 6th power. Okay? The reason we did that is because 4 plus 2 more 3's gives us 6 3's where we're there. All right? So there is the main point of what we are learning in this video, the fact that when we have a number raised to a power times the same number raised to a different power, all we need to do with those exponents is add the two together, and we can have just one expression. All right? Let's see exactly how this is going to look in your practice problem set. There it is right down here. All right, problem 1, which you will find on the top of the next page. top of page 426. Turn there with me, please. All right? Two quick examples that should be relatively easy, then I'll let you tackle those three, and we will move on. Okay? The first problem that I'll ask you to do is right here, 12 to the 4th times 12 to the 3rd. That is almost exactly like what we just looked at on the top, except we have a few different numbers here. But we are still taking some number to the 4th power times that same number to the 3rd power. 12 to the 4th times 12 to the 3rd. We know from our rule up top that all we have to do with that 4 and 3 is add them together, because this one here is 4 12s, and this one here is 3 12s. So altogether, then, we have 7 12s, or 12 to the 7th power. And that's all you are asked to do there, is write it as 12 to the 7th power. Okay? Letter B, very, very similar, except now they've added in that -2 in that power. But it's exactly the same idea. We still have -5 to the 2nd times that same number now to the 7th. Excuse me, this is -5 to the -2nd times -5 to the 7th. Same rule applies, so I'm going to add together my two exponents, -2 plus 7. -2 plus 7 is not 9, it's 5. So our simplified expression here is -5 to the 5th power. All right? Once you feel like you've mastered those two example problems, take a look at those three down there, please. Notice that letter C makes you do it 3 different exponents added all together. All right? Once you've tackled those 3 problems, then we will move on. Go with me to the next slide, and we'll talk about adding some variables in here. But for now, pause that video and look at those 3 problems, please. When you're done, restart, and we will hop to the next page. All right. When variable factors have more than one base, this is a very, very important point. We need to be careful to combine only those powers with the same base. Okay? What that means is, if I have x to the 2nd times y to the 4th, I cannot use my rule for that. Can't use rule. Okay? And it should be obvious why not. Because this is an x and this is a y, and those are not the same base. Okay? Also, please remember here that we have a property of numbers that says we can change the order of multiplication however we want to, and it doesn't change the answer as long as all we are doing is multiplication. You're going to see that come up in the next example. Possibly some things to add to your notes right there. Okay? Once you've added those to your notes, let's go down and look here at problem 2, the other way that this is going to show up in your practice problem set. And now these expressions look probably a lot more complicated to you, right? In letter A, again, I'm being asked to find the simplified form of this expression with all positive exponents, as we know from our last video. And the expression I'm given is 4z to the 5th power times 9z to the -12th power. All right? I want to deal first with these numbers that are out in front of my z's, called coefficients. Now I know that 4 times z to the 5th times 9 times z to the -12th is all multiplication, which means I can change around the way that I'm multiplying this, meaning I can put my two numbers out front and deal with those first, and then deal with my z's separately from that. Okay, so that's exactly what they've done here. They've used these two properties of multiplication, and they have moved the numbers to the front and the z's to the back. Now, 4 times 9 should be easily 36 for you. Hopefully that part is straightforward. The other part is going to be very much like what we did in problem 1, except now instead of having a number to a power 2 different times, now we have a z to that power 2 different times. So we can see here is z to the 5th, here is z to the -12th. We know from our rule on page 425 that all I have to do with those two powers is add them together. So that's what we have done right there. 5 plus a negative 12. And 5 plus a negative 12 still ends up being a negative number. So here we are at 36 times z2 now, the negative 7th power. Okay? Remember, please, that we don't like negative exponents being there in our expression. So we're going to use our rule about negative exponents and take the negative exponent from the top of the fraction, move it right down here to the bottom of the fraction. And our final answer, I will write a little bigger over here, is 36 on the top or numerator of that fraction, and z to the positive 7th power is now in the denominator or bottom of that fraction. Okay? So we went from 4z to the 5th times 9z to the negative 12 to this, 36 over z to the 7th, using those steps. You need to go back, watch that again. Please do that. Once you've tackled that one, we will jump down to letter B, which is slightly more complicated, even though it doesn't involve any negative numbers, because we can see here that we have 3 different expressions that we need to all multiply together. All right? Now, when we tackle part B, the good news again for us is that this is all multiplication, which means we can do it in whatever order we want to. So just like in letter A, I'm going to move all of my numbers out in front. So here we are, 2, 9, 3. All those moved out front. Okay? And then all of my letters move to the back. Now, we need to notice here in these letters that they are not all the same letter, are they? This one is a B. Those other 2 are A's. So I've now put my A's together and my B at the very, very end all by itself, because there's nothing like the B. He's going to be very lonely at the end of this problem. Okay? Once I have my numbers out front, I will deal with those first. 2 times 9 times 3, if you did that all together, 18 times 3, or 2 times 27, should give you 54, which you can see goes right there. And now, when we have 2a, and we see an a right here, a times a to the 2nd, your book reminds you that a, if you don't see an exponent, really means a to the 1st power. So whenever you don't see an exponent, you can always assume there's a little 1 right there. Okay? So really what we're doing is a to the 1 times a to the 2. And again, our rule right here says add those 2 numbers together. A to the 1 times a to the 2 should be a to the 1 plus 2. 1 plus 2 obviously is 3. And as I said before, we didn't get to do anything with that b number. Why? Because it was all by itself at the end of our equation or our expression. Okay? So our simplified answer here actually has 3 parts now. It has a number, an a, and a b. Okay? 54a to the 3rd, that came from our power exponent rule, times b to the 4th, which we had to leave alone. All right? Now again, I have some problems I want you to practice here on the bottom. Once you've mastered those 2 examples, I want you to do these 3 problems right there, A, B, and C. Please notice in part B that you have a C and a D, right? 2 different bases. So just like our rule at the top said, we can only put together the exponents that have the same base. The other thing I want you to know is that remember that if you do not see a coefficient out in front of your variable, like we see right there with x to the 9th, or don't see, I should say, we don't see anything there, we can assume that there's just one of those. So we can put a 1 wherever we don't see a coefficient. Okay? Just like we can put a 1 wherever we don't see an exponent. All right? Tackle those 3 problems. If you have any issues with them, please make a note of that and ask me in class tomorrow. But hopefully, based on these 2 examples we saw, up top, you can tackle those 3 problems, simplifying each one of those down as far as you can. All right? Pause the video, take a look at those 3, then come back and we just have one more example to do, and we'll be all done with this video. Okay, last thing that we're going to do then is go to science class. Ms. Schultz will be very, very happy with us talking about scientific notation here in math class. But this is another way that we can apply this rule that we just learned about multiplying exponents or powers that have the same base. Just as a little background, in case we are not sure of what scientific notation means, scientific notation is used to write very large or very small numbers easily. Okay? We write them as some number between 1 and 10 times, times a power of 10. So, for example, 256,000, instead of writing out that whole number, we would write that as 2.56, so that we're somewhere between 1 and 10 times 10 to the 5th power. Okay? And that's just because we had to move the decimal place over 5 places to get over to here. But you don't have to worry about that now. You just need to know that's what scientific notation is being used for. All right? So now if you will look with me, please, at the middle of page 427, you should see this example right here. It is about water molecules and how many water molecules there are in a certain space of water. So here's what the problem says. 1 cubic meter of water has a mass of 9.98 times 10 to the 5th grams. Then it tells us that each gram of water contains 3.34 times 10 to the 22nd power molecules of water. What they want to know is about how many molecules of water does the droplet of water shown below contain. All right? So here's what we're trying to find. We are trying to find molecules of water. We are given some information about the cubic meters. That's right here in this blue box. We are also given some information about how many grams there are in every cubic meter. That would be right here in this top red box. That's going to go there. And we're also given how many molecules there are in 1 gram of water. That's right there. That's going to go that way. Okay? So all I'm going to do is plug in the information I know, these 3 expressions, into the places that they should go. Cubic meters is here again. Grams for every 1 cubic meter is up here in the top box, and then molecules for every gram is here. Okay? So I'm going to plug those into that equation. I know that cubic meters is 1.13 times 10 to the negative 7th power. And then I'm going to times that by how many grams per cubic meter there were. If you look in your book, you can see that that is 9.98 times 10 to the 5th power. And then I'm going to multiply that by how many molecules are in every gram. We know from our book that that is 3.34 times 10 to the 22nd power. Right? So now I have this expression for how many molecules there are. I want to simplify this down as far as I can. In order to do that, all I have to do is take my 3 numbers, multiply them together. There's my 3 numbers. I can multiply them together, and I will come out with 37.7. And then I'm going to add together my 3 exponents because that's what my rule tells me. As long as I'm multiplying 10 to some power, 10 to some power, and 10 to some power, I can just add those exponents together, and I end up with times 10 to the 20th power. All right? Now, the proper way to write this in scientific notation would be 3.77 times 10 to the 21st power. I would accept either one of those answers. If you know how to change the scientific notation, it's there. Otherwise, you're uptime. Okay? 37.7 times 10 to the 20th. Just another example, another way that you can see this being applied. You do have one homework problem, or I should say practice problem like this. But if you need help with that one, ask me in class tomorrow. That's all for right now. Hopefully this is not too overwhelming for you, but you are ready to start your practice problem set when you get to class tomorrow. So I will see you then. Have a great night.